Hello everyone, my name is Lukas Flohr. I am a UX designer at Ergosign and a PhD student at Saarland University. I am presenting to you today our paper about video-based simulation of autonomous vehicles, which is a joint work with Dominik Janetzko, Wallach, Sebastian Scholz, and Krüger. It is supported by the German Federal Ministry of Transport and Digital Infrastructure. Over the past decades, much effort has been put into the development of automated driving systems that shift more and more control from the human driver to the vehicle. The SAE describes 6 levels to classify the degree of automation. In levels 0 to 3, a driver is still required, whereas in levels 4 and 5, this would no longer be the case. Therefore, levels 4 and 5 are often described as autonomous driving vehicles. While autonomous and especially shared autonomous vehicles have great potential for solving common challenges of today's public transport systems, the technology faces both technological and psychological challenges. From an HCI perspective, key hurdles for the acceptance and adoption of shared autonomous vehicles are users' expectations, concerns regarding the technology's reliability, performance, security, and privacy, and most of all, trust issues. So we asked ourselves the question, how can we counteract these challenges as early as possible? Since autonomous ride-sharing is still a more or less theoretical subject, we figured that we need prototyping and simulation methods enabling us to take this not yet available context into account. For SAE level 0 to 3, SIGCHI-based driving simulators are already very popular in automotive research. They enable the safe assessment of new systems from early development phases on. However, that leaves the question, are those also suited for simulating autonomous vehicles, or are there other potential better options? Since there are no driving-related controls necessary, a promising approach might be to use real-world videos, featuring a very realistic representation of the actual context. These can easily be created and don't require special equipment or programming skills. The idea of using real-world videos to simulate specific situations has already been around for a while. Gray and colleagues, for example, created an immersive video experience in order to put a person into a certain urban context. Chrome and colleagues used a single video to simulate an autonomous ride through a city. Gerber and colleagues combined a pre-existing advanced driving simulator with immersive video to increase the existing simulator's immersion. In contrast to previous approaches, we focused explicitly on simulating an autonomous vehicle with a rather simple and cost-effective setup. Therefore, we transformed one of our office rooms into a cave-like environment, and this consists of 3 front-light video projections, stereo speakers, a seating group, and a single MacBook that controls the simulation. For testing purposes, the setup could easily be extended by HMIs or other components to resemble the interior of the respective vehicle. In our case, we wanted to simulate the experience of riding in a pod-like people mover. To record the footage for the simulation, we used low-budget action cameras, which were mounted on the window of a common car while driving through traffic. To investigate the simulator's potential, we conducted 2 user studies. For the first study, we invited HCI professionals to share their unbiased opinions on the approach. The purpose of the study was to evaluate the general quality of the simulation, to eliminate potential issues, and to derive optimizations. All 9 experts provided generally positive feedback in terms of overall presence perception. Potential for optimization was in particular revealed regarding the sound simulation. For example, participants suggested to add sounds of opening and closing doors, noises from other passengers, or signal sounds for announcing the next stop. Furthermore, 3 participants emphasized the idea of increasing presence perception by adding actors that simulate passengers getting on and off during shared rides. Both suggestions have been directly used for our second study with 31 participants. In this study, we had two major objectives. First, evaluating the simulator with a larger, more representative sample. Second, investigating the effects of actually involving an actor in a simulator study that mimics another passenger. When the participants arrived, they received a short briefing on the study's purpose, the test scenario, and simulator sickness. Furthermore, they signed a participation consent form. All participants took 2 rides in the AV simulator. Each ride took about 14 minutes. In both, the simulated vehicle stopped twice before they reached their target destination. Another passenger joined the ride at the first stop and left at the second. This happened either only virtually, represented by the sounds being heard and the information on the HMI, or also physically, represented by an actor. At the third stop, participants reached the target destination. After each ride, participants filled out a digital questionnaire to assess the dependent variables. At the end of the session, they received a debriefing and their compensation. This video gives a glimpse on how the study looked like when the actor entered at the first stop. After each ride, we assessed presence perception with the IPQ and a single item feeling of reality, technology acceptance with the questionnaire by Van der Laan and colleagues, and well-being by the motion sickness assessment with the motion sickness assessment questionnaire MSAQ and a single feeling of comfort. Descriptive statistics and plots of the IPQ scales revealed a rather positive evaluation of presence perception within both conditions, especially in terms of spatial presence and experienced realism. Inferential statistics did not return significant difference between the conditions. In contrast to the IPQ, results of the single item feeling of reality showed a positive tendency towards using an actor. Paired samples t-tests exposed a significant difference between the conditions. Judging only from the single item, the actor actually seems to have a positive effect on presence perception. Both subscales of the acceptance questionnaire showed a slight positive trend favoring involvement of an actor, but t-tests did not reveal significant differences. However, the tests indicate a non-significant trend with a small effect regarding the usefulness scale. In terms of well-being, the MSAQ generally showed low values in all subscales, with slightly higher values observable in the condition involving an actor. 4 participants explicitly mentioned symptoms related to simulator sickness. Wilcoxon tests reveal significant differences in the subscales gastrointestinal and in the overall rating, also both with a medium effect. The results indicate significant adverse effects on motion sickness during simulator rides that involve an actor. The subjective feeling of comfort achieves high values in both conditions, but without a relevant difference between the conditions. To conclude, we introduced a simple immersive video-based method for low-budget autonomous vehicle simulation that can be used as a prototyping framework. We evaluated the setup with 2 user studies and provide initial evidence for its suitability. Further studies might use the setup for usability testing, user research, or research through design activities. Furthermore, we combined the AV simulator with a human actor imitating a passenger that gets on and off a shared ride. Although we found some support for the idea, it seems not to have a significant positive effect on participants' presence perception that would justify the extra effort. Thank you very much for watching, and goodbye.